15.3, tangents and circumscribed angles, geometry. The essential question: what are the key theorems about tangents to a circle? And you've heard of tangents before, so now we're applying tangents with geometry and with theorems, and it'll get a little bit more theorem-based with the homework, but there's still some application of finding angles, just like in 15.1 and 15.2 for finding angles. So here's the the answer, and I know what you're thinking. That's a huge answer, and I'll go across it, of course. So first things first is I will show you this part. Okay, if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So I will explain that. Also, second, okay, conversely, if a line is perpendicular to a radius at a point on the circle, the line is tangent to the circle. So that's just going the other way with the logic. That's what conversely means. Is we're just going the other way with logic. If A, then B. Well, if B, then A. And that's just what converse is. Okay? But 1 and 2 are basically the same thing. It's just different direction of logic. Now, also, a circumscribed angle of a circle and its associated central angle are supplementary. And that'll be the third thing that I will show you. Alright, so let's begin. First things first, definitions. We have to go across some definitions. A tangent is a line in the same plane as a circle that intersects the circle in exactly one point. So for some odd reason, my snipping here, that's a 1. Okay, 1 point. The point where the tangent and the circle intersect is the point of tangency. So, the tangent line is basically a line that cuts through and it only intersects that circle once. Okay? Now that point where it hits is the point of tangency. Okay? So that's the image in a nutshell. Now in this figure, if we were to do this and we use a compass and a straight edge, which I know you guys love so much, you can actually draw this perfectly, and you'll notice something. You'll notice if you were to do this point to this point, okay, from your center to the point of tangency, and this is where a theorem becomes born, you would notice that it's perpendicular. Therefore, this angle is 90 degrees. Okay? I don't know why it's so messy. My touchscreen must be dirty or something. Okay, 90 degrees. You would notice that. So we're going to talk about that idea coming up. So that idea is the tangent radius theorem. If a line is tangent to a circle, then is perpendicular to a radius drawn to the point of tangency. So that's what I was kind of mentioning earlier in the last slide after I went across the tangent and the point of tangency. Okay? And it's always like that on a tangent. So if the line is a tangent, which again, this line is tangent, it's always going to have from the radius, or I'm sorry, from the point of tangency to the center, a perpendicular line. Okay, so they're always going to be like that. Always. And that's if it's tangent. So in example 1, if both of these lines are tangent to the circle, okay, so this is tangent, okay, right? And then we have our points of tangency, point A, point B, and as we can see, we're coming through the radius. So if you have a tangent and a radius, you can actually apply the tangent radius theorem, which basically just says Well, this guy's 90 degrees, and this guy's 90 degrees. So what does it tell us about the two tangent lines? Well, think about it. Don't we have alternate interior angles? Okay, if we have alternate interior angles, and they're congruent, then you could say that both these lines are what? Are parallel. That's right. So now we're coming across this conversation about parallelism, alternate interior angles. Okay, so this can actually happen. So you can say line A man, my touchscreen is really getting buggy. I think I'll have to reset this thing. There we go. Okay, so these guys are parallel. They'll never cross one another. Okay, so those are little arrows. Okay. So that's where the tangent radius theorem can start to kick in with the logic. And there's some logic-based questions in your homework, and that's just like a little taste, if you will. So just remember, just go ahead and remember that theorem, tangent radius theorem. It's a big one. All right, and again, the converse. So lastly, we said if you have a tangent line going through a circle, then the point of tangency is going to be perpendicular with the center of that circle. Now we're just saying it the other way around. So if a line is perpendicular to a radius of a circle at the point of the circle, so basically they're just saying like the other way. So they're basically just saying, well, if you have a circle and you got the point, the center, all right, and this point right here is the point of tangency. Okay, if this is perpendicular to that, then this line is tangent. It's just saying the same thing that I did earlier with the tangent radius theorem. It's just going the other way with the logic. So now they're just saying, like, if this happens, then this guy's got to be tangent. All right, the other way was saying, the original way that the tangent radius theorem said, it started off with, okay, if this is a tangent, then this has to be perpendicular. That's basically just the logic of this theorem. You can go the other way. It's just letting you know you can go both ways to it in the logic. All right, a circumscribed angle is an angle formed by two rays from a common endpoint that are tangent to a circle. So basically, circumscribed angle, for example, would be right here. This angle is created by two rays, okay, see how they're shooting out, that are both tangents. They just cross that outer circle once, okay? So with this, we can actually apply the circumscribed angle theorem, and it's associated to the central angle, and they're supplementary. So they're basically saying this. So in example 2, let's say we got these other lines created. They're just saying that this angle, angle 1, and let's say this angle right here, angle 2, they're supplementary. Okay, and that's by the circumscribed angle theorem. So again, supplementary add up to 180. And that's always. So I'll tell you what, for example 3, let's apply this logic. Okay, let's say this angle out here, all right, this circumscribed. Notice how it's not inscribed? Circumscribed is outside. Okay, so this guy right here is an outside angle. Okay, so let's say our circumscribed in example 3 is 30 degrees. Now let's just go ahead and find the angle for our central angle. Okay, so I want you to find that for me. So once you find that angle, you're set. And there's a couple problems in your homework that do this. Also, fun fact, this angle right here and this angle right here should also be supplementary. They should both add up to 180. So always remember that. And also, fun fact, they're exactly 90 degrees, aren't they? Yeah, they're both 90 degrees because both those rays are tangent lines. So example 3, that's on you. All right, so there's your homework, page 809 through 812, numbers 1 through 19. This homework's going to be a little harder to chew. Okay, there are some proof problems, I think, some kind of conversation pieces about this. So I want you to work in groups. I'm not there today, I think, but again, just work in groups, see how far you can get. All right, try doing the ones that you guys think you can work with. Talk about it, be productive with one another. You guys are your own resource. Okay, so be respectful, use each other well. All right, good luck, and I'll see you when I get back.